Imagine this. You take just one picture, right? Just one photo of your laptop. And like instantly, that laptop springs to life in a digital world.
Yeah, not just a static 3D model either.
No, exactly. A fully interactable object. You could open it, close it, just like the real thing.
Yeah.
Oh, it's this fascinating frontier we're exploring today, really pushing what AI can do.
And welcome, everyone, to AI Paper Podcasts. We're the place where we unpack the latest, the newest stuff in AI and tech research.
Yep.
Today, we're doing a deep dive into a really, I think, innovative paper. It's titled Generating Interactable Articulated Objects from a Single Image. And it introduces this framework they call DreamArt.
And our mission, like always, is to get you up to speed fast. Especially, our technical listeners, AI researchers, ML engineers, folks who need to stay right on top of these breakthroughs.
Right.
We're going to break down the core ideas, how it works under the hood, and really why this is such a significant step forward for 3D content generation.
Okay, so let's do the quick version first, maybe for the short form clip folks. Here's the 1-minute summary. The basic problem is this: making realistic 3D models of things that move.
Like a laptop opening or drawer sliding.
Exactly. Laptops, drawers, cabinet doors. Doing that from just one single picture, that's been, frankly, a huge challenge. Existing ways, they usually just give you a static model.
Or they need tons and tons of data, right?
Yeah, or, loads of tedious manual work from artists.
Okay, so what's the big breakthrough with DreamArt then?
Well, DreamArt is this new framework that really tackles this head-on. It takes that single image and boom, produces a high-fidelity, interactable 3D articulated object.
High fidelity meaning?
Meaning accurate shapes for all the parts, really realistic textures, and crucially, movements that look physically plausible. Things move the way they should.
Okay, and how does it manage that? What's the magic?
It's basically a 3-stage pipeline. Pretty clever, actually. First stage, reconstruct the object in 3D, but it also intelligently figures out the separate parts.
Segments them.
Right, segments them, and even completes the bits you can't see, like the inside of a closed drawer. It fills in the gaps.
Okay, stage 1. What's next?
Stage 2. It synthesizes a video showing the object actually moving, articulating, and it uses these smart cue things called movable part masks and amodal images to guide that movement very precisely.
Viewable images.
Yeah.
We'll need to unpack that later.
Definitely. And then the final piece.
Stage 3.
Stage 3. It figures out the joint type. Is it a hinge? Is it a slider? And then refines all the textures so the final result looks seamless and, really realistic.
So why should our listeners care? What's the big picture impact?
Well, DreamArt offers a genuinely scalable way to create these dynamic 3D assets. That's huge. It opens doors for advanced applications in embodied AI, definitely AR, VR, robotic.
Basically, anywhere you need a digital twin that you can actually interact with.
Exactly. Not just look at, but interact with.
Okay, that's a fantastic overview. Let's really dig into this now. This challenge you mentioned, image to articulated asset generation, or I2A. It sounds really complex. Why has it been so hard, especially since these moving objects are, everywhere?
That's a great point. They are everywhere. Laptops, microwaves, cabinets. They're fundamental for building, realistic digital worlds, whether you're training an AI agent, creating an AR experience, or simulating robots.
Right.
But the previous methods, they had some serious limitations. Most image to 3D work, it focused mostly on just the surface, the geometry, the texture.
Like making a pretty statue.
Kind of, yeah. They often completely ignored how an object breaks down into parts, and definitely how those parts move relative to each other. The articulation part was missing.
And I know we've talked about things like NERF, Gaussian splatting. Amazing results visually, but they need so much data, right? Loads of different viewpoints or videos of interaction. That seems like a massive hurdle for making lots of assets.
Absolutely massive. Getting all that dense data, shooting an object from every angle, recording every way it can move. It's just incredibly time-consuming and expensive.
Yeah.
It really limits how widely you can use those methods. And before that, the standard was, professional artists spending ages, sometimes weeks or months, manually modeling and rigging everything.
Which just doesn't scale at all.
Not for the kind of demand we see today, no.
Right, okay. So that manual bottleneck. And then you mentioned those drag-based prompts some newer models use. They sound intuitive, like you just click and drag.
Yeah.
But you said they fall short. What's the problem there?
Yeah, they sound simple, but they often struggle with ambiguity. It's a real issue.
How so?
Well, think about it. You drag on a laptop screen. Does that mean slide it sideways? Or rotate it open like a hinge? Or you drag near a complex cabinet with doors and drawers. Which part are you trying to move and how? A simple drag gesture is just, It's often too vague, especially for objects with multiple moving parts.
Like giving fuzzy instructions.
Exactly. You end up with the AI making the wrong part move or moving it in a weird, unnatural way. Inconsistent results.
Gotcha. That makes total sense. So this is the gap DreamArt is designed to fill, right? Tackling these issues with its three-stage pipeline. The goal sounded pretty ambitious. Get the part structures, figure out plausible movements with minimal input, and bake it all into optimized 3D meshes.
Precisely. Let's break down how they actually do it. Stage 1 is all about part-aware 3D object generation.
Okay.
The main goal here is to reconstruct a complete 3D mesh, but not just any mesh. One where the individual parts are clearly segmented, separated out.
Even the hidden parts.
Yes, and fully complete, even if they were, say, blocked from view in that original single photo.
Okay, that sounds tricky. How do they manage that segmentation and completion, especially with occlusion?
So they start by building on top of some existing image to 3D models, which gives them a base geometry. But the key innovation here is what they call mask-guided 3D segmentation.
Mask-guided. How does that work?
They take a simple 2D movable part mask. You can actually get this pretty easily using standard segmentation tools like SAM.
Okay.
But here's the clever bit. This 2D mask isn't just used to crop the image. It actively guides how the faces of the 3D mesh are clustered together during reconstruction.
Ah, so it uses the 2D information to group the 3D parts.
Exactly. It helps precisely separate the movable bit, say, the laptop screen, from the base part. And it's smart about occlusion, too. It can identify mesh faces that correspond to that 2D mask, even if they're only partially visible or not visible at all from the input camera angle. It's kind of like using the 2D mask to see around corners in the 3D space.
That is clever. Okay, and then you mentioned part Amodal completion. That sounds crucial for things like, well, a closed drawer you can't see inside from the photo.
Right. It's absolutely vital for realism. Objects have this amodal information parts that exist but aren't visible in the picture. DreamArt tackles this in two ways. For the geometry, the actual shape of the hitter parts, it uses techniques, they mention hollow part, for example, to basically predict and fill in that missing structure, like figuring out the full shape of the drawer box or the back of a cabinet door.
And the appearance, the textures.
For appearance, they use in-painting models. These models generate what they call Amodal images. Think of these as filling in the blanks, generating the missing texture information for both the movable part and the base part, all from the original viewpoint.
So it's like imagining what the inside of the drawer looks like based on the outside.
Kind of, yeah.
Yeah.
It gives the system a complete visual understanding of the object inside and out, not just the parts you could see initially. It's providing that full context.
Okay, that full visual context seems like it would make a huge difference. Let's move to stage 2. Articulation video synthesis. The goal here is generating a video that shows how the object actually moves, plausibly.
Yep. For this, they fine-tune a conditional video diffusion model. These models are already pretty good at generating sequences that are consistent over time and space.
Right.
But the really clever part here, compared to other methods, is how they condition or prompt this model. Instead of those ambiguous drag points,
They use the mask.
they use that 2D movable part mask directly as an image-based condition.
So instead of just pointing vaguely, you're literally showing the model which part needs to move.
Yeah.
That feels much clearer.
Much clearer. It specifies the intended moving part very directly, which cuts down massively on that ambiguity, especially with multi-part objects. And it needs very little human input, just that initial mask.
Okay, makes sense.
And here's the other key innovation in this stage. Using those Amodal images we just talked about as conditions, too.
Right, the completed images. Why is that so important for making the video?
Because articulated objects often occlude themselves, right? A cabinet door opens, it reveals the inside shelves. By feeding the model the complete, fully visible Amodal images of both the moving part and the base part as extra conditions.
You're giving it the before and after appearances in a way. Or rather, the complete appearance of both pieces.
Exactly, the complete appearance of both pieces, replicated for every frame of the video it needs to generate. This lets the diffusion model focus purely on learning the movement, the articulation pattern itself.
Instead of having to guess what's behind the door as it opens.
Precisely. Without that Amodal info, the model would have to try and hallucinate the newly visible stuff in every frame, which often leads to blurry, flickering, or just weird-looking results. By giving it the full picture up front, the model can concentrate solely on generating smooth, consistent motion.
It's like removing a whole layer of difficulty for the model. Focus on the movement, not the missing pixels.
You got it.
Okay, that's a really neat insight. So finally, stage 3, joint estimation and texture refinement. This is where they really nail down the specifics of the movement and polish the final look.
That's right. First, they actually bring in a vision language model, a VLM.
Oh, interesting. What does the VLM do?
It analyzes that articulation video synthesized in stage 2. Its job is to figure out the joint type. Is the motion prismatic like a sliding drawer? Or is it revolute like a rotating door or laptop hinge? Getting this right is key for physical plausibility.
Okay, so it classifies the motion type. How do they represent that motion mathematically? Sliding and rotating seem quite different.
They use something called a dual quaternion. It sounds fancy, but it's basically a really neat mathematical way to represent both rotations and translations or combinations in a single unified format.
Ah, so it can handle both sliding and hinging movements cleanly.
Exactly, it simplifies the math. Then they use a small neural network, an MLP predictor, to estimate the motion offset for each frame in the video. That's basically the amount of movement, how far it slides or how much it rotates.
So now they have the type of joint, the axis, implicitly from the mask in motion, and the magnitude of movement frame by frame.
Yeah.
They apply that to deform the movable parts mesh.
Correct. But then you have the challenge of putting the deformed movable part and the static base part back together seamlessly, especially considering textures and which part should be in front of the other at any given moment.
Right, you don't want weird visual glitches where they overlap.
Definitely not. They tackle this with a technique called differentiable soft depth blending.
Okay, differentiable, soft depth blending. Break that down.
Think of rendering the base part and the moving part separately, each with its own texture map and depth map, which says how far each point is from the camera. Instead of a sharp cut between them based on depth, this method uses a smooth, differentiable function they mention, using a sigmoid over depth differences to blend them.
So it creates a gentle transition based on depth, rather than a hard edge.
Exactly. It resolves those visibility conflicts smoothly, preventing harsh seams or parts popping visually, giving you a much more realistic composite image.
That's clever. And the final touch.
The final touch is global texture refinement and repainting. This step takes those visually complete part images, including the Amodal bits and the completed meshes, and basically does a final pass to enhance the texture realism and consistency across the entire object, making sure everything looks sharp, coherent, and high quality.
Wow, okay. That's quite a pipeline. So after all that work, stage 1, 2, 3, how well does it actually perform? Did they show it stacks up against the older methods?
Oh yeah, the results they show are pretty compelling. Quantitatively, DreamArt significantly outperforms prior methods like Drag Apart, Puppet Master, and others they compared against.
In what ways?
Well, for the video synthesis part, looking at metrics, PSNR is much higher, like almost 29 versus 23 for Drag Apart. SSIM, which measures structural similarity, is better too, 0.955 versus 0.921.
Okay, higher is generally better for those.
Right. But maybe more telling for, perceptual quality and consistency are things like LPIPS and FVD. LPIPS is way lower, 0.038, compared to 0.068 for Drag Apart, meaning much better image alignment. And FVD, which looks at video quality and consistency, is drastically lower too, like 195 versus 475.
Lower is better there, right? So much less perceptual difference and better frame-to-frame consistency.
Exactly. It means the videos look clearer, more stable, and the motion just looks more correct. And interestingly, they showed that even their version without the Amodal image conditioning still significantly beat the baselines.
Ah, so the core method with the mask prompting is already strong, and the Amodal stuff adds another layer of refinement.
Precisely. And then for the final 3D asset quality, DreamArt also scored higher on things like aesthetic score, MUSAQ, which is an image quality metric, and importantly, in user studies.
What did the user studies look at?
They asked people to rate things like articulation plausibility, does the movement look real? 3D consistency, does it look solid from different angles? And overall quality. DreamArt came out on top there too, showing users preferred its results.
And qualitatively. Did the examples look better? Especially on tricky images?
Yeah, they showed it generalizes really well, even to random in the wild images you might find online. Compared to baselines, which often showed blurriness or weird movements, especially from new viewpoints, DreamArt's results looked clearer, the articulations more plausible, and held up better when viewed from different angles.
So what's the bottom line? Why does it perform so much better? What are the key reasons for this jump?
Well, I think there are a few main factors. First, getting rid of those ambiguous drag prompts is a big one. That directly addresses a major source of errors in previous work.
Right, the mask is just much more explicit.
Exactly. Second, the way they explicitly model the articulation, figuring out the joint type, using dual quaternions, estimating the motion combined with presumably good training data, gives it much better generalization. It's not just pattern matching on pixels, it's trying to understand the underlying mechanics.
And using an explicit mesh representation probably helps with consistency too.
Absolutely. Working with meshes and having these priors about physically plausible motion helps ensure things look solid and move correctly from different viewpoints.
And those ablation studies you mentioned, they really confirmed the importance of the Amodal images.
They did. The studies clearly showed that providing that full visual information for the hidden parts significantly helped the model. It lets the video diffusion model focus its efforts purely on learning the complex motion patterns rather than struggling to simultaneously invent missing textures and figure out movement. It just leads to cleaner, more accurate results.
Okay, makes sense.
Yeah.
But no system is perfect. What limitations did the authors acknowledge? Where does DreamArt still fall short?
Yeah, they put in a couple of things. One key dependency is on the upstream image to 3D models they build upon.
Meaning if the initial 3D shape isn't great, DreamArt can't fully fix it.
Pretty much. Those initial models, while getting better, can sometimes produce geometries that aren't perfectly physically plausible from just a single image. You know, maybe a cabinet door is reconstructed slightly too short or too long. DreamArt inherits some of that potential and initial inaccuracy.
Okay, that's understandable. What else?
The other point is that optimizing articulation based only on a single view synthesized video can still be tricky.
Because you might not see the full range of motion, or there could be ambiguities from just one perspective.
Exactly. Viewpoint ambiguity and occlusions, even in the generated video, can still sometimes make it hard to perfectly nail down the articulation parameters. They actually mention planning to explore multi-view video generation in future work to help address this.
Ah, okay. Generating the articulation video from multiple viewpoints simultaneously could provide much richer information.
Precisely. It's a logical next step.
All right, so wrapping up our deep dive today, what we've really seen with DreamArt is, well, it feels like a genuinely novel framework, a big step towards that goal of getting fully interactable, high-fidelity 3D objects, articulated ones, from just one picture.
Yeah, it tackles some really long-standing problems head-on that focus on part segmentation, using those clever image-based prompts for video diffusion instead of drags, and then really refining the articulation with physical plausibility in mind. Well, that's a very thoughtful pipeline.
And the impact seems pretty clear. This looks like a scalable solution that could seriously accelerate how we create these kinds of dynamic 3D assets.
Absolutely. If you're working in embodied AI, robotics, AR, VR, even just general digital content creation, this could be a huge time saver and capability booster. Imagine quickly generating interactive furniture for a virtual home, or robot training simulations, or assets for an AR application, all from single images.
It really opens up possibilities. So maybe a final thought to leave our listeners with. As this tech gets better and we can create these realistic, movable digital copies just from a glance, what's the next big challenge?
That's a great question. Maybe it's not just generating the objects that move correctly. Maybe the next frontier is enabling AI to truly understand their function. Not just how a drawer slides, but why it slides, what it's for, how it should be used in context.
Moving from generation to genuine understanding and reasoning about physical interaction.
Exactly. That feels like the path towards truly intelligent AI that can interact effectively with the physical world or its digital twin. That's maybe the next grand challenge.